All right, thank you all for coming. Appreciate you all making it all the way to the end. I promise I will try to make this quick so we can all get out of here faster. But, you know, definitely ask questions as we go. I'm happy to take questions as we move through this. This is going to be all about understanding Postgres query plans. The one thing I'm not sure I understand is why you're all here, because there's two other great talks that I'm up against in this last slot that is very frustrating to me. The talk committee did not like me for some reason. My name is Stephen Frost. I'm the Chief Technology Officer at Crunchy Data. I'm also one of the Postgres committers, major contributors, and I've done some Postgres stuff. All right, let's move on. So the way Postgres runs queries is that we construct what's called a query plan, right? These plans are built up using various different nodes where each one of those nodes has a specific kind of job. And what we're going to do is we're going to talk through all the different nodes and kind of how they are used to put things together, to do aggregates, parallel operations, all of those kinds of things. When we are costing using the optimizer, we're going to do two different types of costing. We're going to cost based on how expensive is it to get the very first row from a particular node, and then how much is it going to cost to get all of the rows from a particular node. The reason that we do this is because you know, if you're going to have like a limit or something like that, which is a very commonly used construct in SQL, then we're going to want to have like a fast starting plan, right? So it's all about this kind of, we're going to weigh the question of like, do we want a plan that's fast starting because we're just going to get a few rows based, you know, off the top of a particular sorted list or something, or do we need to more like an analytical type of query where we actually have to go get all of the rows back from a particular node? Certain nodes have more or less the same cost for both of them. In particular nodes where you have to actually see all of the rows before you can start returning any are cases where that's going to have a very similar cost between the two, right? Something like a sort operation. And we'll talk through a bit of that in a minute. When it comes to running explain, right, what you're going to see is that explain is going to give you some information about what the different nodes are. So in this particular case, I'm doing a very simple select. When we see we have one node here, a sequential scan node that is going to be on this PG bench accounts table. Yay, my pointer works on this screen. And here you can see we have the cost to get the first row is basically 0, right? That's because all we have to do is open up that relation and suddenly we have rows there that we can immediately start returning. Now the total cost for scanning through all of the rows here is this 2641.61. Now you might be wondering where that's coming from, right? Well, what it's coming from is the number of rows here, right? As well as information about how many pages we estimate to be in that relation, right? So what we're doing is we're looking at the total number of rows, and that's actually where you're going to get this 1000.61 from. The reason for this is because sequential page cost, so you're going to get is basically, or CPU tuple cost rather, is 0.001, right? So that's where you're going to get 1000.61. The rest of the cost here, right? So you see 1061. So that if we take that out of this, then it's 1641, right? 1641 is the estimate of the number of pages in this particular relation, okay? And sequential page cost is the identity value 1, right? It's the number 1, right? So when we cost this out, we say, okay, it costs 1 unit to read each page sequentially. We estimate 1,641 pages, and then CPU tuple cost is 0.001, and we're going to multiply that times our row estimate. Now the row estimate here is just an estimate, right? This is the estimate of how many rows that we think we're going to get, same as with the width, right? So that's a width in bytes, but it's an estimate, right? That's an estimated average row width, right? Obviously rows can have different width, depending on what's actually stored inside of that particular row. So this is the very basics of a very, very simple query plan. You can then add other options into the explain to get other information back out, right? So, whatever you're adding in options to explain, you're almost always going to be adding in options to get more information out, right? So verbose, for example, will give you the columns that are going to come back, right, from each node. One of the things that's kind of interesting with Postgres is that whenever you have a set of column changes, right, that's called a projection. And we actually cost that out too, because it's not free to reform tuples, right? So, or reform, I'm going to use tuple and row interchangeably. If anybody's confused for any of the language that I use, please feel free to speak up and ask. But so when you have a projection involved, there's a cost to that because it costs some amount of CPU to actually do that. So we may actually keep a larger number of columns coming through the plan than it might actually be required, right? And the reason for that is to eliminate columns, we actually have to do work. So we're not going to do that work unless we need to. And that's something that you're able to see when you add in the verbose option to explain. Another option that you can add is a summary. This is basically just going to add in what the planning time is. So the planning time is distinct from execution time. Now, one of the things I want to point out here is that with all of these explain commands, we are not yet running the query, okay? Explain is a way that you can pass in a query and get back just what our plan is, right? And what our estimates are. We're not running anything yet. And that's where you can see, that's why you can get this planning time. Planning time is a very interesting number because there's always this question of, okay, how much time do you want to spend planning a query versus how much time do you want to spend running it, right? And Postgres, basically the way we deal with that is that we try to make planning time really, really fast. But if you know your query is going to end up being an hour-long query, you might consider increasing some of the options to allow Postgres to try harder when it comes to planning, right? There's a few different options in the optimizer for choosing things like, do we use the Gecko, one of the different types of query optimizations, right? So a lot of it comes down to join ordering. So there's a couple of options. One of them is called the from collapse limit, and the other one's called the join collapse limit. So if you have a particularly hairy query that's joining lots and lots of tables, Postgres will actually choose to potentially switch over to the Gecko optimizer, which is not a total ordering, right? So there's two different ways that Postgres optimizes queries. We use the genetic query optimizer, or we use the total ordering optimizer for total join ordering. Once you cross over a certain threshold, which is like about 12 tables, right, we're going to start using the genetic query optimizer because at that point the total join ordering gets pretty expensive and we want to minimize our planning time, right? So what we're doing there is, what you can do there if you want to spend more time planning is increase your from collapse limit or your join collapse limit depending on how you're doing your joins. So a couple things to look at there. But again, looking at planning time is really informative because you can say, okay, this took like almost 0 time to plan. And so this is, obviously a really trivial query, and so you'd expect that. And where it gets interesting is when you have much more complicated queries. All right, now we're going to talk about actually running the query. When you pass in analyze, that's going to actually run this query, okay? And what we're going to do while running a query under explain is that we're going to time the query, and we're going to time each one of the nodes. And we're going to give that information back to you. Again, actual times here are similar to the costing of how much it costs to get the first row, how much it costs to get all of the rows. And these times are in milliseconds, okay? And here you can see what the planning time was and what the execution time was for this. Now you may see there's a little bit of a difference here between the overall execution time and the time for the sequential scan. The reason for that is that there is some cost when it comes to setting up the executor, and that's what the difference is between these two. Typically, you're not going to see a very large difference between those, though. It's going to usually, whatever the top level node is, it's going to typically be pretty close to what the overall execution time is. Now, one of the things that you don't get when you're running explain analyze is you don't get information about how long it took to get like all of the rows pass back to the client, right? If you want to see timing information that includes passing data actually back to your client, you can enable the timing option in PSQL, right? And then dump that out to, dump the output out to, dev null or whatever. That will then include the actual round trip time. So when you're running explain analyze, that's only going to give you information about what it cost us to run that query server side without actually sending any data back to the client. When we have loops that happen, you'll see it reported here. So when do loops happen? Loops happen when there's a nested loop as part of the plan. We'll talk through the different nodes that Postgres has in just a minute, and I'll talk about that a bit more detail. All right, another option that is really, really handy that I encourage people to use is buffers. So this is actually, a pretty common one that I use, is analyze verbose buffers. So buffers is going to give you back this information here, right? So here you can see shared hits in this particular case. And what that's telling us is that all of the pages that we needed were in shared buffers, right? Other options that you'll see here, it'll say, red equals, 1,000, right? That means we had to go out to the OS and actually read those pages back from the OS. We had to go ask the kernel for those. Now, those pages might be in the file system cache, right? In which case, that might not be very expensive, or they might all have been out on disk somewhere, and it could be very expensive. One of the things that I definitely recommend is enabling I/O timing. If you enable I/O timing, we'll also time how long it takes to read anything off of disk or to write anything out to disk. Now, there is a cost to all of these timing things. If you have a system that's very slow on returning timing information, then you may not want to enable it, or you may start to see skewed information back from like explain analyze output. It doesn't happen very much anymore. It used to happen a lot more on virtualized environments, but it's gotten a lot better lately. All right, so when it comes to the different nodes that you get back and that you're going to see from an explain plan, there's a couple of different things that Postgres needs to do. The first one is that we need to retrieve the data, right? The nodes that we use for that are either sequentially stepping through every record inside of a particular relation. This is called a sequential scan node. It's a bulk operation, and it's typically pretty fast, but it does mean that we have to basically process all of the rows, right? Now, there's also a ability to do a bitmap heap scan, which allows us to do kind of a skipping scan through the heap. This is also very effective, especially if you have SSDs or NVMEs, things that handle random access better. A bitmap heap scan can be quite efficient. We'll talk a bit more about bitmap heap scans in a minute. The other way to get data back from our data files is to use an index, right? And using an index is going to pull specific records back. This is going to be an index scan node. Now, you clearly have to create those indexes generally. Sometimes Postgres will automatically create them for you. If you do something like define a primary key, we will automatically create an index for that. Otherwise, you're probably going to need to create your own. Typically speaking, when you have an index scan node, you're going to actually be accessing both the index and the heap. The reason for this is that Postgres does not keep visibility information in the index, right? So the indexes are pretty compact. They have only the actual index information in them. There's no visibility information. But in order to know what rows we can return, we need that visibility information. The visibility information is in the heap. So as we're scanning through the index, once we find a match in the index, we're going to go over to the heap and look and see whether we can return that particular row or not. Of course, using indexes has the advantage that we can return data in order, either forwards or backwards. And so this is very helpful when you're doing something like an order by. So if you're seeing Postgres having to do a sort because you specified an order by for a particular query against a table, you might want to consider, could I get away with adding an index for this instead of having Postgres do a sort every time we need to get data out of this? If you can add an index for it and we can do either a forward or a backward index scan through it, that's going to be a lot more efficient. The other thing that you're going to see when we're working with indexes is a bitmap index scan. So a bitmap index scan, the way that these two work, this and bitmap heap scan work together. Okay, so a bitmap index scan is scan through the index, find the matches, build up a list of pages, right, and tuples on those pages that we need to go look up, okay? And then once we have that bitmap, we're going to go back to the actual heap and start doing that skipping scan through the heap. Now, the bitmap is sized based on work mem. And if you start to see things like lossy, what that means, like lossy values, when you do an explain analyze on a bitmap heap scan, what that means is that we didn't have enough space within work mem amount of memory to hold all of the pages that we needed to go visit. And what that tells you is probably upping work mem would help. Because if we start to have to do lossy, that means we're looking at more than just the specific tuples that we need. We're having to look at larger chunks of data and then do a filter on it, right? We'd much rather not have to filter. Last but certainly not least, we have an index-only scan. So the way the index-only scan works in Postgres is that we have something called a visibility map. Now, the visibility map will tell us for a given page how much, or if all the tuples on that page are visible to all currently running transactions. So when vacuum runs, which is run by auto vacuum, it will update the visibility map. For every page that it finds where all the tuples on that page are visible to all currently running transactions, it'll make a note in the visibility map saying, hey, if you come across an index that's pointing to this particular page, like an indexed value that says that that tuple is on that page, you don't have to go to the heap, right? Because you can look and see in the visibility map, oh, every tuple on that page is visible to all running transactions, therefore this tuple must be visible to the currently running transaction, and I can just return it directly from the index. That's how an index-only scan works. Now, of course, we may also get to the visibility map and discover, oh, the visibility map actually says that there are rows on that page that are not visible to all currently running transactions. When we discover that, that means we have to actually go to the heap and pull that page back and check the visibility information. So if you're wondering why you're not getting a lot of index-only scans, or Postgres has decided to do an index scan instead of an index-only scan, it's a good possibility your visibility map is not up to date. Because we'll actually look at the visibility map and we'll say, okay, how likely is the visibility map to is going to be able to actually help us with this? So how much of the visibility map is saying everything is all visible to us? If basically nothing is, or if the visibility map hasn't been created because we haven't vacuumed this table yet, then we don't have any choice. We're not going to be able to use an index-only scan, or it wouldn't be effective. So because at that point, you're just looking at pages in the visibility map and then still having to go to the heap. So that's more I/O and therefore less efficient. The next thing about Postgres is that we need to put things together. So the way that we put things together in Postgres to implement our joins is to use either nested loops, merge joins, or hash joins. Right? These are the three main ways that these really the three only ways that Postgres implements joins. Each of these, so I'm going to go through each of these. Nested loop scans, basically you step through one table, and then for each step, you're going to look up a record in either another table or in some other kind of subquery, right? So what this typically looks like is like, the outer one will be an index scan or maybe a sequential scan, and the inner one is going to be a lookup, hopefully an index lookup into another table, right? Now, this is great for small data sets, but it's not very efficient for bulk ones. I am also going to talk about something called Memowise that does help with these nested, parameterized nested loops a little bit later on. It's a brand new thing in 14, or maybe it's 15. Is it 14? I forget. Relatively new. We'll talk about it. Another way that we can put things together to implement joins is using a merge join, right? What does a merge join do? Basically, it expects two sides to be sorted, right? Now that sort can either happen through a subquery or whatever, but more typically it's going to be using either an index or it's going to be doing a full sort on whatever the data set is on each side. And once we have the order, right, both sides ordered, then we can kind of step through it and pop things off of each stack, right? And when we find a match, we're good. Otherwise, we can keep going. Now that's great for bulk operations, but it gets really expensive to sort data. So if an index is available, that actually can be pretty fantastic because you can go in an indexed order through both sides. If there's not an index, we're going to end up sorting the data, and that kind of sucks. Another option is hash joins. Hash joins are very, very commonly used, and what that does is it's going to scan one of the tables, right, and build a hash table with that, and then we're going to step through the other table and bounce entries off of that hash table, right? Now, what this does is it takes a little bit of time to start up, right? It's relatively slow starting because we got to scan that first relation or that first subquery or whatever to get everything we need to put into the hash table. But once that's done, it's very, very fast, right? Obviously, it's pretty memory intensive. One of the things that more recent, more modern versions of Postgres have added is that we have something called a hash mem multiplier option. And what that means is that for most nodes, we only go up to work mem amount of memory. But for anything that involves a hash operation, which includes hash joins, includes hash aggregates, and also includes memoize, because memoize uses a hash table, we're going to use work mem times hash mem multiplier amount of memory, right? The reason for this is that hash tables typically are going to be a lot happier with a bit more memory, and they're a lot more sensitive to spilling out to disk. Each one of these operations can spill out to disk, though. If you start seeing these spill out to disk and you are unhappy about the performance of that query, increasing work mem can help with that a lot, because that's going to encourage, it's going to tell Postgres, hey, you can use a little bit more memory for this operation. If you see like a hash join doing batching or a hash aggregate doing batching, that is when it's spilling out to disk. Merge join, you'll see the sort operations will typically be what's actually spilling out the disk. A merge itself is not going to spill the disk. Same is true for a nested loop. Next thing are aggregates. So these are a couple of the other nodes that you'll see is a group ag or a hash ag. So group ag works a lot like a merge join in that what it requires is the data coming in has to all be sorted, and then we're going to step through all of that information. And when the keys, right, because now we've sorted it all, when the key from the current one and the next one are the same, we're going to aggregate those together, right, those rows together, and keep going. Now that works great if the data is sorted. Unfortunately, though, sorting is expensive. So if you're able to build an index that matches your group by clause, you can get some very, very fast performing group ags. Otherwise, though, if we have to sort it, it's going to probably suck. Sorry, just how it is, right? Hash aggregates, on the other hand, will scan through, and as we're scanning through whatever the table or subquery is to do the group by operation, we're building a hash table, right? And as we're building it, we're checking to see if the keys match on the next record that we see, right? If the keys match, we're going to run the aggregation function and aggregate those values together, and then once we're all done, we'll dump the hash table back out. Now, naturally, this is pretty memory intensive, but it's also very, very, very fast. We then have a number of parallel query related nodes. So Postgres has been able to do parallel queries since 9.6 or so. We actually enabled it by default, I think, in 10. And when you do a parallel query, you're going to see nodes like gather or parallel sequential scan or parallel bitmap heap scan. So the gather node is going to be the top thing, right? The gather node is what is actually going to gather the results back from all of the different workers and combine them in whatever ways we need to in order to run the query. So that's going to be at the top. You'll then, underneath of that, somewhere inside of your query plan, you're going to see one of these parallel node types. So parallel sequential scan will go through and scan rows sequentially where basically the leader node is going to hand out blocks to each of the workers to scan, right? And those workers, what they're going to do is they're going to scan the block that they were given, apply any filters, right? Which is part of how we're parallelizing this, is that we can apply filters or conditionals, right, to eliminate rows and only pass back to the leader the rows that actually pass those conditionals. Parallel bitmap heap scan is very similar to a parallel sequential scan, but instead of being based on just scanning the entire relation, we're doing it based on a bitmap. Naturally, you have to go build that bitmap first and have it available in the leader node in order for it to be able to know what blocks to pass out to each one of the workers. So it's typically what you'll see is we'll do that first, we'll build that up, and then we'll do the parallel bitmap heap scan. We then also have a parallel index scan. This only works on B-tree, but this is basically each one of the workers is going to take turns reading from the index. And what that means is that the results from each worker are in sorted order. So we can have that feed into the leader process, who can then do who can then collate all of that information back. Parallel index only scans are similar, of course, to parallel index scans, but ideally without visiting the heap. Now, as with regular index only scans, if the visibility map is not accurate or doesn't have, if the visibility map says that not all tuples on that page are visible to all running transactions, then we will still have to go visit the heap, of course. All right, a couple of other parallel query node types are ones for aggregations. So how do we do aggregations with parallelism? What we do is each worker can run what's called a partial aggregate, and so that's going to work based on a parallel sequential scan or a parallel index scan or whatever, and it's going to pull those records back and do a partial aggregate on them, right? So you can imagine if you're doing a sum, right, then we can sum all the values from each one of the workers independently, and then the leader node, once it gets the data back, can run what's called a finalized aggregate. And what that's going to do is going to combine the complete the aggregation by combining the results from all of those different workers. Obviously, the finalized aggregate always runs in the leader node. And not all aggregations are able to be parallelized, unfortunately. A lot of them are, though. I do know I'm going pretty quick through all of this. So again, if you have any questions, feel free to ask. A couple of other node types that we have. One really awesome node type is a bitmap and bitmap or. Okay? So remember I talked about where we can scan through an index and build up a bitmap of those pages and those tuples that match our conditionals. Well, we can take those bitmaps that have been built through those index scans, if there's more than one index involved, and combine them in an and or an or, if that's what your query says, right? So this is a case where you have like, select star from my table where A equals 5 and B equals 10, right? In that case, even if you have independent indexes on A and B, we can utilize both of those indexes, right? Because what we can do is we can go build a bitmap from visiting index on A, we can build a bitmap from visiting the index on B, and then do a bitmap and to bring them together and eliminate, potentially a lot of pages from having to be visited. Now this again depends on the bitmap being able to fit inside of workmem, and if we start having to do lossy bitmaps because the number of tuples that we need to go visit is larger than we have workmem amount of memory to save that information, we're going to start reducing the granularity of the bitmap. That makes it lossy, and that also means that we're going to have to visit more things, right? Because maybe, on page 15, there is, one entry where A equals 5 and a different tuple where B equals 10, right? But because the bitmap is lossy, we still have to visit that page. And then once we visit that page, then we'll apply a filter on that page against all the tuples on it and realize that there aren't actually any tuples there that we need. Another node type is a materialized node type. This basically builds a tuple store. And what that is basically we're going to run whatever the query is, store all the results of it, and for later use, and then come back to it and go through it. Right? Now, it's not indexed. It might be ordered. Right? But we still end up having to step through it. Another option is a sort. Another node type, rather, is a sort. And this obviously is going to sort the data back. We have both, regular full sorts, and we can also do a top-end sort where we're sorting, but we know we only need the top, 100 records. So if the record that we are currently looking at is not in that, not bigger than any of the 100 that we already have seen, we're not going to bother keeping that information. We're just going to throw it away and keep moving, right? So that's a top-end sort. Of course, with the sort operation, though, we can't return any records until we've seen all of them, because that very last record might actually be the first one that we need to return, which means that the startup cost ends up being just about the same as the total cost for it. Memo-wise, so this is a relatively new one, but it's really, really cool. So inside of nested loop joins, remember, you have the one side that you're looking at, and then for each row in that one side, we're having to run some kind of subquery or some kind of index scan or something, for each one of those rows. Typically, because what we're doing is it's parameterized, right? So we're trying to, we're looking at this row, it says a equals 5, and we're joining that to this other table. So we need to find the cases where a equals 5 in this other table because we're joining on a, right? So what we're doing is we're going to take the row that says a equals 5 from this table, and we're going to say, okay, we have an entry here. We're going to go look up in this other table for a matching record, right? Inside, typically through an index scan. Memo-wise, we'll save the information, right? It's like, oh, we found this row here, and we parameterized this index scan with this value. We're just going to store this in a hash table in memory. And that way, if we see it again, we can just immediately return it. We don't have to do the index scan again. Really nice, really nice. And that is very often a lot cheaper than rerunning the whole scan. The hash table that it uses, again, is going to be workmem times hashmem multiplier in terms of size. But this is a new node type that is really quite neat. Other node types that you might see, append. So this is, if you're doing like a union or a union all, you'll see an append node, right? It's how we combine the sets together. Limit is what you'll typically see at the top of your overall query. That's going to stop returning records after some number. And whenever we see a limit, again, we're going to work towards favoring those fast starting plans, right? So if you have a limit in your query, you're much more likely to end up with like a nested loop scan than like a hash join, right? Because a hash join, we have to go visit all of the records, whereas with a nested loop join, we can potentially stop early. Subquery scans. Postgres will typically try to take subqueries and take CTEs also, I'll talk about that in a minute, and fold them into the overall query plan, but there are some times where we are not able to actually take a subquery and pull it into the overall plan. In those cases, you'll see a subquery scan. CTE scan, these are for common table expressions. Similar case here. In modern versions of Postgres, we will actually pull in a CTE into the overall query and optimize the whole thing. You can prevent that if you throw a materialize keyword onto your CTE. That'll force Postgres to optimize the CTE independently of the overall query, and that's a case where you'll see a CTE scan happen. So of course, what's the best plan? Well, it all depends, right? The database is going to gather and use statistics to try to come up with the best plan for your query. The way, what commands are being run are analyze and vacuum analyze. And those are going to populate this information inside of PG statistic that is what the query planner is then going to use to plan out your queries. Auto vacuum is what typically is running this stuff for you. You don't normally have to go run analyze or vacuum analyze yourself, but sometimes if for whatever reason auto vacuum maybe hasn't visited that table yet or is busy because you only give auto vacuum so many workers to work with, maybe it hasn't gotten to your table yet, those are cases where maybe it does make sense to run an analyze or a vacuum analyze yourself against a particular table. Very often where I would say run analyze again or vacuum analyze is like if you've just loaded that data, right? If you've done a big copy statement and loaded that data up brand new, go ahead and run a vacuum analyze on it, or at least an analyze. Now, why would you run a vacuum analyze? If you are going to build indexes on that table and you want the table to be able to use the visibility map and get index-only scans, that's going to be a place where vacuum analyze is going to be helpful because vacuum is what actually builds that visibility map. We don't build it automatically as part of a data import. Naturally, if you have bad statistics, you're going to end up with bad plans, right? Explain analyze helps with this because when you run explain analyze, you can see what the results are and compare that against the estimates, right? And if you're seeing like within an order of magnitude, that's usually okay, right? The stats are not perfect. We can't give you exact numbers back. Within an order of magnitude is not bad, right? When it comes to actual values versus estimates, especially when you get a lot of joins happening and things like that, it becomes very, very hard for us to guess and to estimate out how many rows are going to come back, right? But if you're seeing many orders of magnitude difference between the results versus the estimates and you're getting bad query plans, that's where you're going to really want to be running analyze. And you may also want to adjust what's called the statistics target. So the statistics target in Postgres is essentially what percentage of the table do we sample when we're doing an analyze. So when we run analyze, we don't look at every record in the table, right? We sample it. So this is an important thing to understand. You can change how much of the table we are doing that with by changing the statistics target. And I've seen it go both ways. Sometimes increasing the statistics target is helpful. Sometimes decreasing it is helpful. It really depends on your actual data set. Postgres also these days has something called extended statistics. This allows you to define statistics objects across multiple columns inside of a table. This can be really, really handy for correlated data sets, right? Things like zip codes and states, right? Can be very commonly, is a common example of something that's clearly correlated, and by creating an extended statistics object across those two columns, you allow Postgres to collect statistics across the two of them together. Analyze normally looks at each column independently, right? Now, why don't we gather statistics for all combinations of columns? Well, you can probably guess, be really, really expensive to do that. And the more extended statistics objects you have, the harder it is for Postgres to plan that query, right? We have to put more effort into the planning when we have that much more data. Sometimes that works out well, sometimes it doesn't, right? It really depends on your queries. So here's what it looks like to view a join in Explain. So this is clearly a simple nested loop join where we have a sequential scan on the branches table and a sequential scan on the accounts table. Why did Postgres pick this one? Well, in part because this branches table only has one row. Postgres, when it estimates there's only going to be one row, has a tendency to say, well, only one row, nested loop is going to be great for this. Problem is, Postgres sometimes gets that wrong, right? We've gotten better at it, but there are definitely cases I still see these days where, like, we're doing a bunch of joins, and we get up to the top, and because all of those joins in Postgres' mind were reducing the number of rows up, it got in its head that, we're going to get back like 0.0003 rows, right? Now, you won't see that because we're going to cap the minimum at 1, right, in terms of our estimates, but then we're going to end up doing a nested loop join, right, potentially, and that could suck. But again, we're working on getting better. Anyway, so it's going to do that, and then it's going to scan the accounts table. Now, naturally, if there really is only one row, well, that's great, right? Nested loop scan is perfect. You can force Postgres to look at alternate plans. I don't really recommend doing this because it's very brute force. But if you're curious about, like, well, why do we pick that plan over this other plan, it can be helpful. So here what we're doing is we're using these enable options to disable nested loop. Now, it doesn't actually disable it, right? If nested loop is the only option for how to run this query, we're still going to run it with a nested loop, right? It's just how it's going to go. But it's going to be very, very expensive. And that's really how this works, is we just are making these very, very expensive. But here, after we've done this, you can see that instead, we're going to use a hash join, right? Now, look at this cost here, right? This cost is 4,018.47. And if we go back, you can see that it is indeed a higher cost than the nested loop join. So we know the reason we picked the nested loop join is because Postgres costed it out to be cheaper. So when you're playing around with things, you can change things like random page cost, you can change things like CPU tuple cost, and you can see what the impact of those changes has on things like on these cost values that get costed out. Here's what a hash join looks like. You can see the hash condition, and you can see the actual hash table being built here. So Here we're doing a sequential scan on the branches table. We build a one-row hash table, and then we scan the accounts table, bouncing it off the hash table. So you can also disable hash join as well and do it again. And this time we're going to see a merge join, which is clearly much more expensive. And the reason for that is because we're doing this big sort down here, right? We're doing this big sort because we need this BID to be sorted to do this merge join, because we're joining on BID, and there's no index on BID in this particular table. Now, when you run and explain analyze with a hash join, you get more information. This is true for a lot of things, because when you're actually doing we're actually running the query, we're going to have more information that we're able to provide, right? So here you can see I enabled buffers. So here you can see 2,000 of the pages that we needed were in shared buffers. The other 161,000 were pages that we actually had to go out to the OS and read, right? Which means that they were not in shared buffers, so there's a cost there. And here you can see we did a sequential scan on PGBench accounts, and here you can see the shared hit for this sequential scan was 2,112 and 161,000. So these the buffers up here are accounting for the buffers of the nodes underneath, right? So we're not reading 4,000 buffers here, okay? We're not hitting 4,000 buffers in the shared buffer cache. We're only hitting 2,000, right? This top level buffers count is the total count. The other thing that you can see, though, that's really nice is this information about how big the hash table was that we ended up building, right? You can see how many buckets we had, how many batches we used, and what the memory utilization was. Now, again, this is a case where if you're starting to see multiple batches happening, that's very expensive, right? That means that we ended up having to spill the disk, essentially, for the hash join. You don't really want to do that. And so that's a case where you definitely want to think about maybe increasing work mem. Not the case here, but you can see here we had buffer counts again for this information too. And we have total planning time and overall execution time. So when you're looking at parallel plans, this is a bit more complicated, right? So I mentioned the gather node before. Here you can see how many workers we planned and how many we were able to actually launch. Postgres, when we do a plan, we come up with how many workers we want. But when we actually go to run the query, we may not actually be able to launch that many workers due to max connections and other constraints on how many workers we're allowed to launch. And so Postgres will be able to run the query with however many workers we are in fact able to launch, including if we're not able to launch any. The reason that this works is because the leader always also participates in the query plan, right? So when we're looking here, we see 2 workers planned, 2 workers launched, but these numbers here, right? So these numbers and these number of loops, the number of loops in a parallel plan is actually the number of workers that are working on that node, right? And the number of rows here, you can see, is a pretty convenient 1/3, right, of the total number. And the reason for that is because we actually have 3 workers that are working on this. We have the leader process that is working on it, as well as the 2 workers that were launched. And here you can see we're doing a merge join. We have a sort, and the sort is over top of a parallel sequential scan. So we're doing a parallel sequential scan. Each one of the workers is then sorting the results of that and feeding that up into a merge join that then returns the data back to the gather node, and back to the leader process. So this is just the top half. The bottom half looks like this. And what this means is that because this is a regular sequential scan, that means that that was actually run in each of the workers. So each of the workers did their own sequential scan and their own sort. And we did that because this is a tiny table, right? There's 96 rows, right? So it's very inexpensive for each one of the workers to do that, and then they can have the merge join be run in parallel, right, by each one of them, right? So each one of the workers is running its own merge join, okay, and then feeding that data back up. All right, so a really, really cool site to look at a lot of this, to look at query plans is explain.depez.com. Unfortunately, I don't really have a lot of time remaining, but maybe I'll pull it up if there aren't any questions to go through it. But first I want to ask, are there any questions? Yes? Yeah, we can let the, yeah.
Does explain have any cost?
Does
Explain
Have any,
cost?
does explain, so.
Just
not
running explain, does it cost?
Yeah, so when you run explain, right, just explain without running explain analyze, right, just the explain is going to have the cost of doing the query planning, right, which if it's a really big complicated query is going to cost some amount of CPU utilization to go and read that in, right? Now, to do like all of the calculations of join ordering and stuff. So it's not free, but it's not going to actually go access any of the tables or read any data off of the regular relations. Now, when you run explain, it is going to go read all of the statistical data, right? And it's going to have to go read in the information about all the different tables involved from the catalog caches. So there's a little bit of cost there, right? But it's pretty nominal, right? Most of what you really are going to see is when you run an explain analyze, that's going to actually run the entire query, and that gets expensive. There's another question I saw over? Yeah. Yeah.
So when I read the plan, do I read from the bottom up?
Yeah. Typically, you would read kind of from the farthest and indented and from the bottom up. Yeah. In terms of if you're thinking about what's the order of how things are kind of operating, that's typically how you would look at it. Yeah. Now, realistically, though, each one of the nodes is gonna. That was interesting. Is gonna return records, right? Especially like an index scan, right? If you have an index scan feeding into a nested loop, the index scan is running and the nested loop join are running at the same time, right? Because the index scan is producing rows, and every time it produces a row, that's going to go up to the nested loop. That's then going to come around and do probably another index scan, right, on the other table. So things are happening at the same time, but if you're thinking about kind of like where the data is coming from, that's going to be the furthest in, right? Because we have to go get the data first before we can do anything with it. Whether that's a sequential scan or whether that's an index scan or something like that, that's going to be the start of it. And then it's going to feed up into we call it like a volcano type of planner. Yeah, does that help? Yeah.
If I'm using prepared statements, am I saving the planning?
Yes, you are. Okay. So yeah, if you do an actual proper prepare and then an execute on each one, and you do that multiple times, you are saving some amount on the planning. Now, this gets a little tricky, all right, because the way that Postgres works, and it starts to involve questions about do you have partition tables, right? If you have partition tables, there are still some things that we're going to do at execution time to try to make the most effective use, right, and come up with the best plan. But okay, this gets slightly complicated. Postgres has the notion of generic plans, right, and then specialized plans. Okay, so by default, the planner will try and will actually do. So you'll prepare it. That'll give us a generic plan, right? When you actually start executing that query and passing in actual literal values into that plan, we're going to perform kind of a quick replan, right, for the first 5 times. And then we're going to compare the cost of that replanned query against the costs that we came up with for the generic query. If the costs are more or less the same, right, we'll use the generic query. And if they end up being more or less the same or the generic query is somehow better, it's not typically the case, but if it ends up being the same for those 5 times, then after 5 times, we're not going to bother with that anymore, right? We're just going to keep using the generic plan that you gave us. If, on the other hand, the specific plan that we come up with ends up being a lot cheaper, right, based on our costing, then we're going to continue doing that kind of half replanning each time you give us a new value, right? Where this typically becomes really relevant is when you have a partition table or something like that where we're doing a lot where the values that you're passing in are allowing us to eliminate a whole bunch of tables, right, from having to be considered, right? And that's going to make the cost go way down really fast, and so we're going to continue doing that. But overall, yes, it's valuable to prepare your queries. I think it's the long and short of it, if that helps. Did that answer your question?
One more. Last question.
We've seen cases where for certain columns that don't have a lot of different values.
Oh, neat.
So for example, we have a tenant stripe column, and if there aren't a lot of tenants, there's only 2 different values in that column.
Right, you have a low cardinality, yeah.
Correct. We've seen cases where if I don't bind that column and actually have the exact value in the where clause, the planner does a much better job than if I bind it and, gets a question mark in the query. Does that make any sense?
Well, I think it would be interesting to see what happens. I mean, is that, now that, I mean, I don't know if you knew about the 5-time thing, but now that you do, I wonder, is it like, are you doing this for thousands of queries? And so if you're doing this thousands of times, I'd be curious to see what the first 5 looked like. And it might be if you you can actually do an explain on your prepared queries. You can do and see what Postgres planned for that, what the generic plan was for that, and that could be helpful and informative, right? And it might be that what you're seeing is that we're doing this costing of each one, and we think the genetic one's going to be better, but it ends up not being, right? And when we do the other one, we end up just always using the specific query plan for the particular value you passed in. Also, though, I mean, I don't know what the query plan structure looks like for those, but if you're seeing things like nested loops, that's actually where memorize is going to be really, really helpful for those kinds of cases. Because we can do a if we're doing a parameterized lookup in that other table, and we see the value come back, if there's only 2 values, and we can hash those, like, it's going to be great, right? And we're not going to have to redo that look every time. But it depends a lot on the specifics of the query. So I'd have to look at the particular query to be able to help more on that.
Awesome. Well, we are out of time, and thank you, Stephen.
Awesome. Thank you all.